Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Hakim Nadzmi bin Abdul Rahman, and today I will be presenting my final year project 1 proposal, which is kinematic analysis of FSAE car suspension system. My supervisor is Prof. Madya IR Dr. Amir Radzi Abdul Ghani, and my co-supervisor is Prof. Madya TS Dr. Ramzyzan Ramli. Okay, let's begin. For today's agenda is project summary, introduction, methodology, and expected results. To summarize, this project focuses on designing, analyzing, and fabricating the suspension system for UiTM FSAE car that complies with FSAE regulations. The suspension system will be analyzed using MSc Adams car software to determine suspension behavior when subjected to dynamic conditions. So, what is the role of a suspension system? A suspension system is to provide a stable platform to control the vehicle. It also protects the chassis and the driver from the shock jolts as the car goes over bumps or uneven terrain. Suspension system also helps to keep all the vehicle's tires in touch with the road surface. It dampens the natural oscillations caused by the rubber tires, springs, and uneven surfaces. Suspension accomplishes this by locating the wheels in a precise geometry relative to the vehicle utilizing links and structures. The behavior of the wheels and chassis when accelerating, braking, and turning is determined by the geometry of the suspension. Suspension is divided into two types, which is dependent suspension and independent suspension. Dependent suspension system is the system in which two wheels are connected to each other. For example, if one of the wheels is disturbed by bumps, the other wheel will be affected. As a result, right and left camber wheel change is the same. As for independent suspension, each wheel moves independently without affecting the movement of the opposite wheel. As a result, right wheel camber change does not affect left wheel. This is a few examples of dependent and independent suspension. Under dependent suspension is satchel link, Panhard rod, WOB link, Mumford linkage, and leaf springs. For independent suspension is swing axle, sliding pillar, McPherson strut, double wishbone, and multi-link suspension. For a suspension system, there are several suspension parameters that are involved. Firstly is the camber. Camber or camber angle is the angle between the vertical axis of the vehicle when viewed from the front. Camber angle can be differentiated into three, which is positive camber, neutral camber, and negative camber. Positive camber is when the tires are pointing away from the vehicle's center line. Neutral camber is when the camber angle is 0 degrees, and negative camber is when the tires are pointing inwards to the vehicle's center line. Camber angle is crucial to maximize contact patch of the tires during cornering. Secondly is the caster. Caster angle is the angular displacement of the steering axis from the vertical axis of a steered wheel in a car. Caster angle is very important in terms of steering effort, cornering, and stability. In any vehicle, positive caster is applied to ease the return of the tire to an upright position when coming out of a turn. F1 cars have at least a few degrees of positive caster angle. Thirdly is the toe. Toe angle is the direction of the wheel pointing upward or inward from the centerline in top view. There is two types of toe, which is positive toe and negative toe. Positive toe is when the tires are pointing inward, whereas negative toe is when the tires are pointing upward relative to the car's centerline. Toe is necessary for car's directional stability and tire wearing angle. Next is kingpin inclination. Kingpin inclination or KPI is the imaginary line drawn through the kingpin as viewed from the front or rear of the vehicle. KPI is said to produce vertical displacement of the vehicle during steering in an upward direction as the vehicle is cornering. KPI also produces scrub radius. Scrub radius can be adjusted by changing KPI. The problem statement for this project is how the suspension system of the race car responds to various driving conditions during all the familiar SAE tests. And for different tests in FSAE competition, there will be different parameters set up for the car suspension system. This will lead to second problem statement, which is what is the optimum suspension parameter setup. The objective of this project is to perform kinematic analysis of suspension system for FSAE car to achieve an optimum performance in different conditions of FSAE tests. Secondly, is to perform simulations to observe the effects of change in suspension geometry, caster, camber, and toe has on the car's behavior. Thirdly is to achieve the best suspension parameter setup. The scope of work for this project is to perform kinematic analysis to observe the suspension behavior when subjected to different driving conditions. Secondly, MSc Adams car software will be used for dynamic simulation changes of kingpin inclination angle, caster angle, camber angle, front wheel toe angle, and ground point lateral slip amount of front wheel. As for the limitations of this project, firstly is the lack of experience among FSAE team members. Secondly is the limitations of physical meet and discussion among team members, and to retrieve lab data for related analysis due to COVID-19. Moving on to methodology of this project. This is the methodology flowchart of suspension system development. The design of suspension system will be followed using this flowchart. The design of suspension system is an iterative design process. Iterative design refers to the process of designing, testing, analyzing, and refining until desired result is obtained. Initial step in the procedure is to gather information about the related study. Then, product design specification will be created to meet the project requirements. After that, a model geometry of FSAE car suspension will be created in MSc Adams car software with suitable type of suspension chosen. After the design is complete, kinematic analysis on suspension system of FSAE car will be performed, specifically parallel and opposite wheel travel simulation. After getting the result, a few parameter adjustments will be made for iterations. This cycle will be repeated until the desired result is obtained. Next is model geometry. Front and rear suspension geometry will be created in MSc Adams car software using custom template. Hard points coordinate will be retrieved from previous UiTM FSAE car. So the first step is to create a template in template builder. Then assign the hard points coordinate to build suspension parts which are upright, spring, damper, control arms, toe and camber variables and hub. After that, create and define attachments and parameters which consist of joint and mount. Lastly, assemble the model and perform the analysis. These are the front and rear suspension hard points coordinate retrieved from the previous UiTM FSAE car. As you can see on the top left, those points are the hard points of each suspension components assigned and created in MSc Adams car software. Moving on to the top right is the opposite wheel travel simulation on suspension setup. Lastly, on the bottom is the example of Adams car suspension test rig. And for our last agenda, the expected result of this project is to create an optimum and improved design of suspension geometry from previous UiTM FSAE car. Analysis on suspension behavior will be performed to determine the best suspension setup for UiTM FSAE car 2022. So different suspension parameter setup can be made for different FSAE tests to achieve the best performance. A set of suspension preliminary design has already been provided by previous UiTM FSAE team, and it is the baseline for the next design process and further analysis and iterations. Finite element analysis of UiTM FSAE car suspension system has already been performed to analyze the strength of the suspension components. That's all from me. Thank you.